My name is Irina Overeem. I'm the Deputy Director of CSDMS. For those of you who haven't met me, welcome. One of the cool things of CSDMS is we all think about the Earth's surface. But that means that you can think about the Earth's surface on like a grain scale where like you're moving bed load around. Or you can think about the Earth's surface as mountain rising and like mountain building. And those like vast scale dimensions mean that it's hard to like sort of make one uniform model that would do it all. And that's one of the reasons why we have this like more component-based, flexible modeling framework in which people can connect processes for their specific research questions. What it also means is that these keynotes will be over vastly different scales and over vastly different processes. It can be marine, it can be weather, it can be long-term landscape evolution. And so one of the joys, I think, of the CSDMS meeting is that you get to hear from the other side of the scales quite a bit. And some of the like really new collaborations that resulted out of like CSDMS meetings, etc., often have to do with connections that people would normally not make within their AGU session or in their like more specific domain. So with that, it's my honor to like introduce the keynote speakers for today, and you'll see that these are like over a variety of scales. The first speaker this morning is Gaia Stucky de Quay. She's at MIT, and she will be talking about global flood volumes on Mars and insights into a persisting water cycle.
I just want to make one announcement for the speakers. I have two options, handheld mic or an over-the-ear mic. The trick with the handheld is you have to talk into it like this. So let me know which one you want. I'll have both available. And also, there's a clicker to advance the slides, or you can use the keyboard. So which one do you want? And just remember to keep it.
Okay, can everyone hear me? Is this distance okay? Perfect. Awesome. Thank you so much for having me here today. I had a joke prepared about how we were going to start on Mars and then focus on a real planet, but Irina gave a really nice intro as to why we're doing that, so I'm not going to say that anymore, and I'm basically just going to go straight into it and show you a little bit about how we can look at the erosional record of Mars, particularly looking at floods, and use that to actually try and understand how persistent these habitable climates that we know existed on Mars, how persistent they actually were over time. And so it doesn't matter if you don't know a lot about Mars, because I'll give you a quick primer as time allows, but today Mars is very dry, very cold, and in terms of surface processes, a little bit boring. But when you go back about 3.5 to 4 billion years ago, it was a much more dynamic surface and much more like the surface of the Earth. And there's huge amounts of evidence for what was going on Mars in terms of this water cycle. So I'm going to focus on a couple of different ones. But you can see here, you've got these, doesn't work, these valley networks, which are these deep canyons that were carved by these fast flowing rivers, much like the rivers we have on Earth. And then on the other side of the source to sink spectrum, you also have all the sediment that was deposited in these large standing bodies of water, either forming deltas or alluvial fans that we can observe. And that's just what we see from the satellite perspective. When you look in situ at all the rover data we have, the evidence for water, persistent water on Mars is equally compelling. So things like rounded pebbles, cross beds, ripples that suggest that there was ice-free lakes, all sorts of things. And so we have all this evidence to suggest that there was water, and we know there was water around 3.5 billion years ago, abundant, all over the surface. But one of the outstanding questions that we're still trying to address and place more quantitative constraints on is how long was water available on the surface of Mars? And so not just the total amount of time for the total time that it took to carve a valley network, for example, but each individual episode, when it did rain or snow and melt, how long did these specific episodes last? Because at the end of the day, this determines whether the surface was habitable, because at the very same time, we had Earth, which was starting to also develop its own life form. So understanding these timescales is important for understanding whether we will ever even observe any form of past life on Mars or present. And so for this talk, again, I'm going to be focusing on the erosional record. And so when we think about erosion on Mars, especially around this time of very heavy, very intense precipitation, which was, again, 3.5 billion years ago, you can kind of split them up into two categories. The first one I mentioned briefly, valley networks in black, you can see here. Again, analogous to the rivers that we have on Earth that are persistent and they're formed from either rainfall or snowmelt. But then we've got these white ones that you can see here, and those are these lake outburst canyons that form at the end of these lakes that are outlined and shown in blue. And so these are more analogous to lake, I guess, dam breach floods on Earth, where you've got a huge lake that is impounded either by a man-made dam or something like a landslide, and then something fails or there's overtopping of that topographic obstacle, and then you get a huge flood. And so one of the questions is, well, how do we know these are outburst floods? First of all, morphologically, they're very different. They're very wide, they're very deep, but I'll take you through schematically how we think these happened. On Mars, you have a lot of craters, like in all of the other planetary bodies except for Earth, because Earth has plate tectonics. But on places like Mars, you're basically littered with craters. And craters aren't just a topographic depression, they also have these elevated rims, which essentially act as basin confining topography. So what that allows you to do is to build up all this huge amount of water in this crater, and then once you get that overtopping, you cause this huge erosion from the breaching of that elevated rim from the crater, resulting in an outlet that we can observe. And so you can kind of think of this as two different volumes. So you've got the volume of the flood, which is in blue, and then that volume that is brand new volume that is eroded when that flood breaches. And so what people have done in the past, and notably Tim Gouge led the study in 2019, where he went and collected a subsample of something like 24 of these open lakes on Mars, or purported open basin lakes on Mars, to then compare, well, if we look at the flood volume in blue, and we also measured the outlet erosion volume, are they linked? Are they actually proportional to some degree to each other? And he found that, yes, they are. So this kind of led to the idea that these must be essentially primarily formed from that flood, because the volumes are so similar. And so another way to think about the volume of the flood, which we'll get into later in the talk that I just wanted to introduce, is that flood volume that is sitting there in this crater has a potential energy. And if you remember, your basic equation for potential energy is just your mass and your gravity and your height. And so you can kind of rethink that mass as the volume of the flood. So it's essentially similar to the metric of the volume of the flood, with the added information that this lake is kind of higher up to the rest of the plateau. And so that's another way you can think about this. Essentially, just measure that potential energy, and we find that, again, same relationship as you would expect. One is a metric for the other. But the cool thing is that this allows us to actually compare the values for Mars and for Earth. And we see that both do follow a sort of linear in log scale relationship, showing that, of course, one is related to the other, but also it kind of shows you the scale of how much bigger these floods are on Mars. And so the other thing I wanted to quickly introduce here is, why are we focusing so much on these lake outburst canyons? Well, the reason for that, at least on Mars, is that if you measure all of the eroded volume on the surface of Mars, about a quarter of this volume is from lake outburst canyons. So this is a huge geomorphic driver on the surface of Mars that really carved out huge, huge canyons. And also, these are places that are essentially determining where habitable conditions form. So we do want to understand how they form and if they persist or not. And so the kind of question I'm going to be answering is here, how do we take these lake outburst canyons and how do we use them to figure out how persistent these habitable climates were? And so the way we do this here that I'm going to take you through is, what if instead of focusing on how well this relationship performs and how nice this linear relationship is, why, and following this line here, why don't we focus on how badly it follows the relationship? And in particular, focus on these points where there is actually a much larger outlet erosion than there should be given the size of the flood. So for example, for places that have a very large outlet erosion, but a small flood volume, that means that something else had to carve the rest of that canyon. And so potentially there was some more flood after, some more flow after the flood that caused that canyon to continue eroding afterwards. So you want to answer, is this true for any of these systems? How many lakes experience this? And can we actually calculate the amount of water? And so this project is kind of split into 3 parts. The way to think about these 3 different parts is, first of all, we want to build a more global, more complete global catalog of floods. So the small sample I showed you had about 24 lakes that were all mapped manually. So first we want to see, can we add more points to this plot to better understand that relationship? Second part is, what if instead of just doing a best fit line, why don't we actually figure out what the theoretical relationship between these two should be to actually understand whether they're following the line that they should be? And then the third part is then how do we take this and quantitatively place constraints on hydrology on Mars? And so this is actually work that is not led by me, but is led by some of my group members. And it actually turned out to be a really nice collaboration because my grad student, Zoen, did the first part for her first year of her PhD, and then Chuanchi, my postdoc, did the rest of the work and is leading the manuscript write-up as I'm speaking, and hopefully we'll be submitting this soon. But I'd love any feedback you have about this at this moment anyways. So the first part is to build a global catalog of flood volumes on Mars. And so, because it's a short talk, I don't have time to go through all the technical details of how we did this, but please feel free to ask me either in the questions or afterwards. But the main idea is that you've got a full lake level when the crater was not breached. So you can kind of see that as the blue outline in this 3D image, and then the full lake in dark blue, and then overtopping happens, you then get erosion of that breach, and then you have a new lake level because all of that water has exited. And what we then want to do is to find out what is that dark blue volume that was released that led to the final lake level then happening, because most of these lakes did not drain fully. So they kind of stopped at some point, usually between 50%, 80%, 50%, 20% are pretty typical numbers. And so we did this semi-automatedly for the whole surface of Mars for every single open lake that we could find, which gave us about 200 data points. So an order of magnitude more than we had before, because before they had been done manually. And so what that gives us is a map that looks like this. So this is a global map of all the flood volumes that were released on Mars. And for a little bit of context, because these numbers don't really mean much on their own, but if we look at some of the mega floods, so Lake Bonneville was one of the largest mega floods that we had on the Earth's surface. And so that plots somewhere at the higher end of that scale. And then if you go even further back in time, geologically, some putative results, maybe 10 to the 15 meters cubed for the Zanclean flood, which is the one that filled in the Mediterranean, plots at about there. So these are huge floods, akin to some of the largest floods that we've ever had on Earth. So that kind of takes care of the first part. We've now got an updated new database of global lakes on Mars. And that the first part here is the blue part that we've filled in. We now have all these lake volumes, but we also have from a previous work that we worked on with Tim again, 2021, we also have that orange part. So for every one of these lakes, we have the outlet erosion volume as well, which we calculated using a method that I don't have to talk about here because I don't have time again. But we basically have everything we need for the Mars part. And then the next thing is, well, if we want to assess the relationship, first we need to figure out what do we expect the theoretical relationship for these two to be? And for that is unfortunately where we have to go back to the Earth and use data that is on Earth, because Earth is data rich and we've got a lot more constraints on what is going on. And so what my postdoc did is he went through all of the literature he could, and he tried to find all of the dam breach floods on Earth where we could actually measure not only the flood volume, but also very accurately constrain the outlet erosion volume. And he thought he would end up with a very big database like the one that we have on Earth, but actually he could only find these 4. And the reason for the small sample size is that he really wanted to have, potentially a DM difference map where he could accurately constrain that VO, outlet erosion volume, but also he wanted it to be very recent floods because you don't want there to be post-flood contribution to the erosion of the outlet. So we want the outlet to only have been eroded by the flood. And so this is what we end up with, 1 in Chile, 2 in the US, and 1 in China. And so what do we then do? Well, let's think about what this relationship between the flood volume and the erosion volume should be. Again, we're going to be thinking about this in terms of the potential energy. You'll see later why. But let's say that there is some theoretical relationship between the erosion of the outlet and the potential energy of a lake. And they're proportional to some constant that we're going to call K for now. So again, you remember potential energy can be expressed as this, where we've got the volume of the flood, but also this height. And we're going to call this drop height the entire height that the water drops from the very top of the lake all the way to the bottom of the canyon, to also kind of get the drop height all the way along the channel, which sometimes is used only as the small distance from the breach point to the final point there. But we can use these interchangeably. And then that gives us an expression for the potential energy that we can fill into our theoretical expression. And so we get this expression that says, well, the outlet volume should be proportional, should be equal to these constants. And the great thing is that we can measure all of these, or, we have the density of water and gravitational acceleration. We can measure the slope of the channel and the length of the channels. That's another constraint we had for our Earth examples. We needed to be able to measure the slopes and the lengths of the channels. So that's why there weren't so many. But that's great, because what we can then do is solve for our K. So for Earth, we can figure out what is this K value that relates how the outlet erosion is, how its relationship to the flood volume. And again, a high erosion efficiency, similar to the stream power K, means that you erode more efficiently for a given amount of water. And so amazingly, even though the slopes and the flood volumes and outlet erosion volumes vary over multiple orders of magnitude, our K values converged into less than 1 order of magnitude for all of these different locations. And so that was really exciting for us. And, probably because we used such a very small, tailored number of places where we really could constrain these values more accurately. And so what that means is that we've now got an erosion efficiency on Earth. And what we then do is convert this into an erosion efficiency on Mars by taking the largest one. We're always trying to be more liberal so that we overestimate flood erosion, and that'll be more clear why. But there's a little bit of calculation there where we also put in we take some effects from numerical models which suggest how sediment load can vary under different gravitational acceleration. So we just multiply that by a factor of 4, which is what this study suggests, to put that in there. But we're always being liberal. We're always trying to push our K to be as big as possible for Mars. And so we end up with an erosion efficiency for Mars, which looks like this. And so that's great, because we now can say, well, this is the model outlet erosion that we expect given a K, but we can also observe outlet erosion for all of these 200 lakes on Mars. So that means that we can just subtract these 2 outlet erosions, and what this will give us is a volume that cannot have been carved by the flood. This is a volume that had to be carved after the flood was formed. And then finally, these are the kind of assumptions that you can do on Mars, but you probably wouldn't do on Earth. But because we don't have as much information on Mars, we do it. But given a rock volume, we can convert that into a water volume by simply assuming a water to sediment ratio of a value that's usually used for Mars and some rock porosity. But essentially what that gives us is a water volume that must have flowed after the floods happen in these outlets. And so what we can then do is calculate that, and we end up with a distribution that looks like this. So you can see here, this is the total volume of water after the floods for about 3/4 of our lakes. So 3/4 of our lakes, their outlet volumes could not be explained by the flood alone. So that's a huge amount of erosion that happened even after the floods. And even if you calculate the amount of water, most of the water actually happened, you can see here, 98% as post-flood water relative to the relative small amount of water that happened during the floods. And so another question you may be asking is, well, is there any actual physical evidence for this post-flood water you would expect there to be? And actually, when you go in and you look at the lakes that show no evidence, or you wouldn't expect there to be post-flood water, you don't see anything in the canyons other than a canyon. And then for about half of the lakes where we have it is suggested that there should be post-flood water, we actually find a lot of terracing. So you can see here, there are these inner channels that happen within the canyons themselves, suggesting that there had to be a little bit, at least a little bit, but probably a lot of water happening after these floods. And so we actually can generate some DMs to potentially in the future calculate these volumes just from these elevation models as well. And so the main idea of this is, we know this part. We know that a crater forms, a lake can then form, erode into the crater, and that there is flooding. But what we're trying to show is that that's not the end of the life cycle of one of these crater lakes. So, you can have some drying or not, but you most certainly have, for at least the majority of these lakes, significant post-flood flow, meaning that these lakes could have been stable for much longer. And ironically, Jezero Crater, where the Mars 2020 rover is now, is actually not one of the lakes that had post-flood flow. So it actually only had enough water to overflow, and then that was it. So not as much water. But these are the kinds of things we didn't really know before, and certainly explains why we're finding limited evidence of lake sediments. And anyways, the main idea is that, this overflow flooding of a lake was kind of thought to be this culminating event. You barely have enough water to fill in these lakes, they overflow, and that's kind of the end of the life cycle of this water on Mars. But really, these systems did flow for much, much longer than we used to think. And we're trying to place constraints on the amount and then the timing of this, and hopefully better understand what would be some good future candidates to explore on Mars. And that's it. Thank you. Yes.
All right, thank you. It was a great talk. So I don't know the methodology, but I'm assuming you used the morphometrics of the river channel to sort of find out the volume of water which might have flown through these channels. Am I correct? Or was it something different?
We essentially just use the volume, the carved volume of the valley, and then just use a sediment to water ratio to convert that into a water. That's as much information we have on Mars.
Okay.
Well, yeah, there's more if you've got depositional systems, and people have used, deltas and fans to determine runoff rates and all of that. But we basically just have a carved canyon, and that's pretty much it.
So I was just wondering, since you don't have much atmosphere on these planets, but there is this space weathering happening, which kind of has modified these planets or these, the topography on Mars, for example. And since not much water has flown on Mars for several 100 million years now, how would this weathering impact your assessment or, your assumption of how much water would have flown through these channels? I don't know if it makes sense.
And it's not just space weathering. There's a lot that's going on, and it's not even hundreds of millions. It's 3 billion years of everything happening on Mars except for water. So you've got impact craters that are modifying the surface, space weathering. You've got, you still have got hill slope and a lot of landsliding that happens afterwards. There's a lot. And so the way to think about it is in terms of the relative contributions of each of these. And for a lot of these canyons, they're hundreds of meters deep. And even if you take the largest, guesses of how much aeolian deposition or hill slope relaxation you could have, these would give you a few, maybe tens of meters of difference in the elevation. So there are ways to then add in, okay, well, what if we remove this amount of volume, this contribution of volume, because it was deposited in? So we can remove that. But at least for this study, because we're looking at there's definitely some stuff that can be done in the supplementary, but because the scale of these canyons is so large compared to the other contributors, it's less important. The other big one to mention is glacial modification, which as Mars got colder was more important, but that's why we kind of tend to avoid, when we're looking at fluvial geomorphology, we tend to avoid going 45 degrees towards the poles. So we stick to the equatorial belt But that's definitely a huge consideration in every Mars paper is all the 3 billion years of everything else happening. And you just have to think about the scales and make some estimates for what could have changed.
Thank you, Gaia.